Next, we have Max Grossman from BP, and they're going to talk about their data science sandbox.
The co-authors on this presentation are Keith Gray, who's the director of high performance computing at BP, and Stefan Gerard, who's here in the audience, who basically built the Center for High Performance Computing brick by brick, and is also the infrastructure lead for the data science sandbox. My name is Max Grossman. I'm the lead on data science efforts within the sandbox, which includes both evaluating hardware and software platforms for data science problems at BP, as well as building out data science projects on behalf of business units. So today I'm going to be talking about the data science sandbox, which is, in a nutshell, a research and development platform for solving BP problems with advanced machine learning techniques. This talk is kind of looking at three audiences, which means every one of you is going to be bored for 2/3 of it. But basically, I want to talk to both technical folks who are interested in the infrastructure and the software that we're using, business folks who are interested in the practices and the processes that we're using, as well as students who are interested in getting a feel for what are the opportunities for data science like in Houston and kind of what is BP doing in this space. I'll start with a little motivation. Some of you might just be kind of nodding your heads. This is obvious, but I still think it's important to cover. The sandbox, kind of like a lot of efforts probably in oil and gas in data science in Houston, came out of probably some VP or some executive going to a talk like one of the ones we had this morning, where we all got really excited about data science and how data was building these massive new companies, and then kind of went back and said, we got to do this. And then it was kind of our job to figure out how. But the problem with that is that the successes that have happened in machine learning and advanced data science so far have largely come in domains that don't look anything like oil and gas or the energy industry. So for example, the Amazons and the Googles and the Microsofts often have very relatively clean data sets. A picture of a dog is a picture of a dog. You didn't have 30% of the photons headed towards the camera intercepted by a salt deposit or something like that. At least I don't think so. Whereas in the energy industry, we're generally dealing with very dirty, messy time series data, 3D volumes, lots of things where noise is a very significant problem. In general, we've seen successes come when you have a large corpus of well-labeled data. So the image nets and the other kind of data sets that you see lots of academic papers published on. In the energy industry, usually there isn't even a truth. I can't tell you where a salt dome is because BP didn't go excavate a square kilometer and then figure out actually where the salt is in the earth. Even if there is a truth, often the data set isn't labeled or isn't thoroughly labeled. So if you're talking about fossils in rock cores, I don't think most people have a labeled data set that says where every single fossil and every single rock core is that they've pulled out of the earth for the last 30 years. So again, we've got this complete different domain with completely different characteristics that presents problems for the kind of supervised machine learning that folks have had a lot of success with. And then in terms of talent, I think in general, dealing with uncertainty and statistical uncertainty in both downstream and upstream is an area where oil and gas companies don't generally do too well and haven't done historically in the past. The Amazons and the Googles and the Facebooks, they have legions of PhDs in computer science and statistics and mathematics to support their domain scientists in linguistics and other things. And in general, we don't have that. And then finally, and I think maybe most importantly, there's a big difference in the cost of getting something wrong. So if you label a dog as a cat and you show me a search result that has 99 pictures of cats and then one picture of a dog, that doesn't cost me anything, and you still get your half a cent in advertising revenue. But if you get an answer wrong in energy or in other kind of high-cost industries, you could be talking about that one answer driving millions of dollars of investments. And so that kind of ups the ante on explainability. It ups the ante on just trusting your models and being able to understand why they're giving you the answer that they're giving. So one approach that we've seen internally and at other companies that people use in order to try to transfer these successes is to take commercial product A, apply it to some vaguely described problem B, and then immediately fail. Sometimes this can work. You can take the Google Auto MLs and apply them to some regression problem internally. and have it turn around and give business value. But a lot of times it just doesn't pan out. And in the end, even if it does, you're left with a completely undifferentiated solution relative to your competitors. Now, everyone can buy Google AutoML, and it doesn't matter if you've solved this problem using it, because everyone else will. Another and possibly even more common approach is to take more of a consulting practice where you contract out to some external company based in San Francisco or somewhere like that, describe to them a vague problem which they have no domain expertise on. They're just a bunch of really smart guys in machine learning or computer science. Give them this vague problem, spend 6 months trying to get them some redacted data set that doesn't give up any of your private IP, doesn't give up any of your personally identifiable information, and then try to work with them to couple your domain experts in geosciences or geology or finance with their expertise in statistics and machine learning. And generally, this doesn't really work out that well for you. They get to learn about your domain, certainly, but in our experience, a lot of times it doesn't lead to some successful model that you can then deploy into production and drive business value from. So oftentimes this doesn't work. You really need that tight coupling of internal expertise and strengths with the external expertise in machine learning. So what we've tried to do is build an internal solution. And kind of the fundamental assumption that we're driving off of is that a really successful model for building data science or solving data science problems successfully in oil and gas is to combine these 4 things together. So first, you do need internal data science and machine learning expertise. That's me. You do need domain-specific expertise. So that's your existing pool of geophysicists and geologists and finance guys and IT guys that already know your systems and know how to work with them. And then you need a flexible R&D environment that brings them together. So the worst thing you could do is have the first 2 components and then invest $2,000 a year into your compute and your software and everything else, because then you're not going to be able to solve anything. So you need to be able to try out kind of weird stuff where you're not sure if it's going to work, and try it at really large scales on the order of thousands of processes if you need them. And then finally, and this part can also be overlooked as well, is you need a driving set of processes. So some kind of a steering committee that keeps these really smart guys from veering off into a corner with 0 business value. Keep them working on problems that are both valuable but also tractable. Not like, not say we're going to do completely automated seismic interpretation by 2020. Like that's not a tractable problem. You need to break that down into things that you can actually solve. So the Data Science Sandbox is BP's solution to this problem. It's a specifically research and development, so we're not a production environment, a specifically research and development platform for advanced machine learning and data science at BP. So we are both a platform where other people can come in, bring their expertise, bring their understanding of Python or R, and solve problems on our platform. But we're also a team that goes out into the business and talks to folks who aren't statisticians and aren't computer scientists and aren't kind of computational scientists, and solve their problems for them on their behalf with a very close collaboration. Like I said on the previous slide, we are driven by a steering committee with organization-wide vision into kind of what's going on in machine learning at BP, who are the people that have problems that could be leveraging our expertise and our technologies, and then also make sure that we're aligned with other strategic initiatives in upstream and in downstream, just kind of being a barrier to us going off into the weeds and losing focus. Then most importantly, we do have a ton of close collaborations with a wide range of internal customers who tend to be extremely focused in their area of expertise, whether it's seismic processing or kind of pressure modeling, safety, different things like that. And then we work very closely with them to learn their domain and then to share our domain with them. So that's certainly one big problem that I called out earlier is as education is a problem, is getting the energy industry up to speed on statistics and machine learning and all these kind of techniques around uncertainty. And so we kind of encode that into all of these engagements by sharing what we're doing, why we're doing it, how we're doing it, using things like Jupyter notebooks and just slide decks with pictures on them. We do things like multi-day hackathons in order to kind of kickstart projects. We have weekly check-ins with these kind of internal customers in the business units. And it's an exciting way to kind of learn about, BP is kind of its own self-contained country with all these different industries and business units internally that you get to work with. When we talk about the sandbox internally, we usually split it up into 3 components: hardware, software, and people. So I'm going to talk through those. For the technical folks, I'm going to talk through those a little bit. The substrate of the sandbox, which Stefan is responsible for primarily building, is a large network file system. We also have kind of network mounts of other file systems within BP, but we have our own networked high-capacity file system on which we can store anything. So this goes back to the investment thing. You have to be able to invest in being able to store these multi-terabyte data sets if you're going to actually work on them. On top of that, we have probably nothing too surprising. So we have kind of a standard pool of x86 machines that can be used to spin up small Jupyter servers on or other things. We have access to GPU machines, both Kepler and Pascal-based machines, where we can run your standard kind of Keras and TensorFlow. And then we have big memory machines with anything from 128 gigabytes up to a terabyte of memory. And so these are really important. I'll talk about this a little bit because in our experience, the Python and R frameworks for distributed machine learning can be a bit flaky and certainly a heck of a lot more difficult to manage. And we don't have enough resources for a full-time, 10-man IT team to manage these clusters for us. So having these big memory machines allows domain scientists and data scientists to work on their problems at the full scale, not with some tiny little data set that has no meaning, and to do that with purely shared memory and in-memory platforms and software. And then on top of that, we spin up an infrastructure that probably doesn't look too unfamiliar to anybody here who's working in data science. So we're a heavily Jupyter-based platform. We're heavily based on open source and free software, and we try to support that by kind of sending out issues or submitting pull requests when we can. In general, the most common usage mode for our users is to basically just spin up a Jupyter server through our Jupyter Hub interface, which authenticates with our central authentication server. Spin that up on a standard x86 machine, and then go to work on some data that we've imported for them into our high-capacity file system. More advanced users, of course, will be using either Dask or Spark in order to run problems where the data set doesn't fit in one of those big memory machines, and they need that generally extra memory capacity. It's pretty rare that we run into a situation where they go out to these clusters for the extra compute. Usually it's my data is just too big to fit into the memory of one machine, and so we spin off these Dask and Spark clusters for them dynamically on an as-needed basis. And then on top of that, we're using all of the kind of standard modern data science frameworks, the TensorFlows and the Keras and the gradient boosting and the Pandas and the Plotlys, and et cetera. And the team, so the core team is the infrastructure specialists who are responsible for managing the hardware and the software and make sure everything runs smoothly and is up to date. We have a number of data scientists who support either testing out new software that we might be interested in using for projects or supporting directly other business units in executing their projects on their behalf. So these are folks who are, for example, experts in safety on rigs, but they don't know anything about statistics or machine learning. And so we get to go work closely with them and explore how machine learning can work for their problems. And then we also partner with a lot of external advisors. So some of these are just folks in BP that we know really well and talk to a lot in the HPC, in seismic processing, in all business units. And some of them are external kind of third-party vendors who we have hardware from them or we use software from them. And so we work very closely with them. In terms of project selection, so kind of getting back into the how do we manage all of this from a people perspective, we generally select projects based on these 4 categories. As a small team inside of a very large company, there's always way, way, way more work than we could ever get done with the people that we have access to. And so we have to filter down those projects by some metrics. Usually the first metric, of course, has to be business value. This has to be a real problem, not an academic one that delivers actual value to BP. Tractability, I can't tell you how many conversations we have with someone who attended a conference like this one, got really excited about machine learning, and then comes to us with some really vague, gigantic problem that we could never solve in a decade. And so oftentimes, our problems have to be tractable. Often those those conversations lead to tractable problems. But the first step is getting that person to drill down on, what is the first step in this pipeline, this magical dream, and how do we get there? The third one, which is maybe the most important, is having a stakeholder who's bought into this project. So somebody in the business unit who actually is willing to stay engaged with you, have these regular chats, and then when you come up with a solution that works, they're actually willing to try it out, maybe run it alongside their existing workflow to see how the results compare and gain kind of confidence in the results and make them more comfortable with these techniques. And then sometimes we do take on projects which maybe have less business value, but offer us an opportunity to build out a new capability. So for example, maybe we've never done a project in text processing, and a new project come along which allows us to demonstrate that capability and to build out experience with the latest kind of platforms and software for those kinds of problems. And so we'll take those projects on as well. Now, I'm not going to go into too much detail on any of these projects, but I wanted to give folks a feel for the width and the depth of the projects that we're working on at BP. And so this is just a sampling of the projects that we're working on in the subsurface. And so you'll see a lot of things here that are from, you'll recognize from previous talks today and from the HPC conference and from previous data science conferences. So for example, Shell gave a great talk previously about picking out faults automatically using machine learning talks. So these are just a sample of our projects that are more subsurface focused. We also work with more operations focused projects where you're dealing more with active operations, and these tend to be a little bit more focused on time series and text processing data, where you're looking at predictive maintenance or failure prevention and things like that. And then also just some kind of internal business focused project where we're looking more at kind of internal processes and helping to automate them or identify where bottlenecks are and different things like that. I am going to be able to go into a little bit more detail on a couple of these projects. So the one that we've worked on relates to applying 3D machine vision frameworks to rock cores. So rock cores are little chunks of the earth that you pull out of wells, which you can then use in order to better characterize your reservoir by basically running different workflows and analyses on these rock cores. Today, these workflows are extremely complex, manual, and time-consuming. So it takes a geologist again, it can take a day to run this workflow. And the problem is they're tied up, and also these workflows can be a little bit subjective. You're tuning thresholds, and you're figuring out exactly based on their eyes and their experience, what's the right way to process this rock core. And on the other side, the noisy kind of data, the complexity in the data means that you can't just set a simple threshold. You can't just say that everything that looks like this in the rock is a pore in the rock, and everything that looks like this is a grain. You've got very nonlinear, complex relationships between the different segments of the rocks and what they actually manifest in the physical domain. So we've gotten a lot of experience applying modern computer vision frameworks to this, leveraging kind of state-of-the-art hardware, GPU-based machines, working very closely with external vendors to take their very latest releases and apply them to our problems and see, do they help or do they hurt, how they affect performance and convergence and these types of things. So this is a great synergy of just big data sets, noisy data sets, and the latest state-of-the-art in software and hardware in order to solve an actual business problem. We also, sitting in the CHPC, obviously do a lot of work with seismic data. So this project has really stressed the kind of distributed Python capabilities of the data science sandbox. We see, obviously seismic data is very noisy, particularly around salts and other things. We're exploring kind of opportunities for pulling the noise out of that data by expanding it essentially into as many dimensions as possible. So basically, rather than trying to filter out noise in the 3D or 2D dimensions that people can actually process it, try to explode that into as many dimensions as possible and see if there are some dimensions or some combinations of dimensions where we can separate the noise from the signal. Run into a lot of challenges. I think the biggest challenge here is just the scale of the data and the processing that's necessary. We have had pretty bad experiences with a lot of the Python distributed frameworks in terms of processing this data and being able to run machine learning frameworks on them without running out of memory or running into other stability issues. There's the challenge of converting from whatever seismic data format the data is stored into whatever format your machine learning frameworks know about. And then, of course, it's required just a lot of face-to-face, back and forth meetings of, hey, I saw this in the data set. Does this make sense to you? No? OK, well, let me go back. Let me retweak that. And going back and forth with geophysicists to try to figure out if the things that you see make sense to their kind of expertise. So with that, I'll wrap up. In summary, basically what we want to do is come here and just kind of share what we're working on, make sure that everyone's aware that BP is doing cool things in data science, and we love to hear what you folks are doing about so that we can use it internally, whether it's your tools, or your software, or your hardware, or your ideas. We're hoping to share more today and over the coming years. This is kind of the sandbox, which is the home to machine learning at BP. Thank you.
In the interest of time, we'll take one quick question.
I noticed that most of your use cases seem to be upstream data science applications. Can you speak to any downstream refinery-oriented projects?
So we're just starting to get a lot more into that within the last month, basically. We have been very upstream focused, mostly because we sit in the CHPC, which is a seismic imaging focused kind of center, and most of our friends just happen to be in upstream. But we're getting more into like the predictive operations and maintenance on valves and sensors and things that you see in plants. But I can't really talk about anything too specifically.
Thank you.